Alright, this is going to be an acid-base workshop that's going to give us a thorough introduction into the acid-base module. So the first thing we want to discuss are, of course, what is an acid and what is the base. And we're given actually three different definitions to describe an acid or a base, and they all basically will refer to an acid or a base. That means it does not matter which definition you use to describe a compound that is an acid. If it's an acid, it will be an acid regardless of the definition used to describe it. So the more common Arrhenius definition will define an acid and a base in terms of the ions they produce in solution. Acids will always produce an H+, bases will always produce a hydroxide. And then we move on to, alright, well, what other ways can we describe an acid or a base? The other is that an acid is a hydrogen donor, meaning H+ has been donated. Well, it has an H+, so it can donate it. Well, in turn, a base will then accept it, so it's a proton or hydrogen acceptor. So, again, it's complementary. One donates, one accepts. The final definition, which is the Lewis definition, describes an acid or base in terms of whether they will donate or accept an electron. Well, if this is a proton and it's a donor as an acid, and then it should be an electron acceptor. And if a base is a proton acceptor, it should be the electron donor. So just basically the opposite. Notice how they're complements of one another. Where there is an acid, there is a base, because H+ and OH-, again, the hallmark equation for an acid-base neutralization reaction is that we form water, which is a neutral product. So that being said, we're then going to take this one step further and recall that we have some ways of course, showing what kind of ion has been produced, and that is through a chemical equation. For example, HCl, a strong acid. So again, you need to know what your strong acids and your weak acids are, and what your strong bases and weak bases are. That's very important in this module. Memorize the strong ones through the notes and what's been given to you in terms of what the strong acids and bases are, and then you will be able to know which ones are weak simply by default. So let's take a look at H+. H+ here is the result of H and Cl breaking up. So HCl will break up into H+ and Cl-, and these two will be aqueous. If this was a base, such as sodium hydroxide, a strong base, then we would be looking at a dissociation to form Na+ and hydroxide-. Notice how we have an H+ coming from the acid and an OH- coming from the base, because every acid-base neutralization basically forms a salt and water. So that being said, then we want to take a look at, alright, well, what are the strong acids and bases, and which are the weak ones? So H+ with chlorine, bromine, and iodine. Those three halogens, and only those three, will make a strong acid. H+ and NO3- nitrate, SO4 2- sulfate, and ClO4 1- perchlorate will also make a strong acid. That then tells us, alright, well, what else could we possibly have that could be an acid? Again, anything with H+, but if it is anything besides these 6 acids, then you know that it's weak. So if you know these 6, you'll know the strong ones, and by default everything else will be weak. So let's take a look and see what our strong bases are before we move on. So bases, again, are going to have hydroxide. So any group 1 or 2 metal, so you look at the periodic table and look anything from group 1, sodium, lithium, cesium, and so forth. Group 2 metals, magnesium, calcium, and so forth. Group 1 or 2 metals, with only one exception being beryllium, will give you a strong base. So, for example, sodium and hydroxide will give you sodium hydroxide. If you have something from group 2 like calcium, which is a 2+ with hydroxide, that will give you calcium hydroxide. Again, notice we have 2 hydroxides there for every 1 calcium, 1 hydroxide there for each sodium because of the plus charge and the 2+ charge. So again, making sure that you have the correct formula is going to be very important in not only writing the formula, but perhaps some of your calculations. Okay, so let's move on to looking at what we call the pH scale. So of course the pH scale is a way of determining how acidic or basic a particular solution is. And it basically is a number line. And what we're going to have is on this number line, somewhere in the middle will be 7, and that is the neutral point. pH scale runs from 0 to 14. Now, if we're going to be looking at pH here, anything from 0 to 6.9 in this area here would be an acid. Anything above 7 to 14 would be considered a base. Now, the further away from neutral, meaning the 7 that you go, meaning the higher the pH, then the stronger your base. The lower the pH, the stronger your acid. Now, we can also look at this from a pOH scale, which you may have heard of or may not be as familiar to you. It's simply the reverse or the complement to the pH scale. So instead of 0 over here, it's 14, and instead of 14 here, it's 0. 7 still stays as a neutral. Think of this as like a piano. If you go up in one direction, meaning from the left to the right, the sounds get higher pitched. As you proceed from right back to left, the sounds get lower in pitch on a piano. And so they have corresponding notes. It's just that depending on whether you're playing a key on the right side or on the left side of the piano, you may have a higher or lower pitched version of that note. So if I'm now looking at the pOH scale, a pOH that is between 7 and 14, meaning a high pOH, would correspond to a pH from 0 to 7, meaning a low pH. So a low pH and a high pOH are indicative of an acid. By the same token, a low pOH, meaning from 0 to 7, a low pOH is complementary to a high pH, and that will indicate a base. So looking at it from either a pH standpoint or a pOH standpoint, you can actually determine the relative strength of an acid or a base. Again, the lower the pH, the stronger the acid. The higher the pOH, the stronger the acid. The higher the pH, the stronger the base. The lower the pOH, the stronger the base. Again, notice that this is a complementary system. As your acid gets stronger, your base gets weaker. As your base gets stronger, your acid gets weaker, and so forth. So while all this is great, what we really do need to do now is do a quick little example here whereby we look at some numbers, because we like to quantify values. So let's say we had a pH of approximately 3. Again, here's the middle point. So here's 0, here's 14, a pH of 3. This would of course indicate that we have an acid, and it's actually relatively strong because it's pretty low on the pH scale. Now, if I was to say, all right, what is this on the pOH scale? Again, instead of 14, it would be 0, and instead of 0 here would be 14. So, somewhere between 7 and 14 would be the pOH value. And that pOH value is a complement to 14. So 14 minus 3 is 11, and that is the pOH value. 3 is equal to the pH. The difference between 14 and 3 is 11. That's the pOH. And so, again, whether I have a pH of 3 or a pOH of 11, that indicates that I have a strong acid, because what this would mean is there's an increment of 1, 2, 3, all the way through 14. What this indicates is that this is 0, so there's an increment of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This right here is 11. These two values are basically saying the same thing. One is saying it in terms of pH, and one is saying it in terms of pOH. Let's quantify this even further and put in some equations. How do we determine what the pH and the pOH of our acid or base are? Obviously, we're looking again back at the definition, the first thing we discussed, which is that the concentration or amount of hydrogen ion produced in a solution of an acid should basically indicate the strength of the acid. Or the concentration of hydroxide in a solution should indicate the basic strength of the actual base. So we're going to look to see how concentration of hydrogen ion and hydroxide ion will affect pH and pOH. So what P generally means, this P value, and it's very important to make note of that, simply means log, L-O-G. And what this actually is telling us is a negative log. Because when you take the log of these concentrations, you will inevitably get a negative value. And since pH and pOH can't be negative values, we need a negative to negate the negative we get from here. So this is all it means. So if I said pH, it simply means the negative log of H plus. pOH simply would mean P is negative log of OH. Let's say P of X would be negative log of X. So just think of P as negative log. Alright, so now that we have basically our pH, pOH equations, let's take a look and see what we're going to do next. Alright, now that we have pH as being the negative log of H plus and pOH being the negative log of OH minus, let's take a look and see what these values can actually be. Of course, the concentrations that you get for H plus and OH minus, again, that's what the brackets represent, is concentration. You will simply plug into your calculator, take the log value, you will get a negative number, take the negative of that negative, basically flip the sign to a positive, and that will tell you your pH or your pOH value. Of course, we know that the pH and the pOH scale do what? End up to be 14. So if you know pH or pOH, and of course you know they add up to 14, that is definitely a way to go about finding out one versus the other. So if you have pH, you can very well calculate pOH and vice versa. And again, what these values tell you is the inherent strength of your acid or your base. And where are they coming from is the relative concentrations of your H and your OH, what we use to define these. So let's take this one step further. What if I actually had the pH and the pOH and I wanted to find the concentrations? I wanted to reverse these equations. Let's take a look and see how we can do that. Let me just put these back up here. pH is equal to negative log of H plus. pOH is equal to negative log of OH minus. And if I added those two together, I would get 14. What if I wanted to reverse this, meaning rather than take the log, I wanted to take the anti-log? So if you're not familiar with what an anti-log is, simply it is, instead of log, which is log to the power of little 10, it's big 10. It's 10 to the x power. This is called anti-log. So if I wanted to take the reverse of this, instead I wanted to solve for h plus using pH, it would be 10 to the negative pH. Simply I'm dividing or moving the negative sign to the other side. That's how I'm getting a negative pH. And I would take the negative log here, and I would get rid of it by taking the anti-log, and I would do the same thing on this side to the pH, and that's how I get 10 to the x. X is your pH value, or your pOH value. So H plus is equal to the negative 10 to the negative pH power. By the same token, if I wanted to find just the hydroxide concentration, it would be the hydroxide concentration is equal to the anti-log 10 to the negative pOH. Again, I've moved my decimal and I've taken the anti-log. So X is simply your pH or pOH value, and that is how you're getting 10 to the negative X. So whatever your value is for your concentration of hydrogen or hydroxide, that is what you put to the negative power for 10. If you wanted to then switch this equation, you would take the negative log of pH, that would give you H plus. You would take the negative log of pOH, that would give you OH minus. And you would take the negative log of 10 to the 14, which is 10, again to the negative 14. So there you go. Now you've got 1, 2, 3 more equations. If you're looking for concentrations from pH, there you go. If you're looking for concentration of hydroxide from pOH, there you go. And now, just like if you know pH or pOH and you know they equal 14, you could find one from the other, you know that H plus times OH minus is equal to 10 to the negative 14. Again, 14 being the magic number here in the pH world. So if you know H plus or OH minus, and you know, of course, they equal 10 to the negative 14, you can then definitely use one to figure out the other. Incidentally, this value of 10 to the negative 14 we call Kw, which is the ion product or constant of water. So let's recap very quickly. And that is pH is equal to negative log of H plus. If I wanted to reverse that, I could say that H plus is equal to the, let's do this, 10 to the negative pH. pOH in turn is equal to the negative log of hydroxide, which then means if hydroxide is to be determined, that is the 10 to the negative pOH. If we were to add pH plus pOH, that would be 14. So if I wanted to reverse that, it would be H plus times OH minus, because we're doing the log scale. Instead of adding, we're multiplying, just like exponents. That would equal Kw, which is 10 to the negative 14. And from there, we can take this even one step further into looking at Kas and Kbs. So we've talked so far about strong acids, but what about weak acids? Well, weak acids don't dissociate 100%. For a weak acid or a base, when they don't dissociate 100%, that means they actually dissociate hardly at all. And a good way, of course, of spotting a weak acid or base not only is, of course, knowing your strong acids and bases that we've listed previously and knowing that anything besides those is weak, but also look for your double arrows. This indicates a weak electrolyte, which also means weak acid or base, such as HC2H3O2, which is acetic acid. And that dissociates to form H plus and your acetate ion. You may have seen the acetate ion also written as such. Either one will work. Or let's say a very common weak base which is ammonia, NH3. A lot of people don't spot that as a weak base because it doesn't have the hydroxide calling card. Well, if you actually add water to it, you can get NH4 plus and hydroxide. So it doesn't necessarily use the Arrhenius definition of, hey, it has a hydroxide in it, but it does indeed use the Arrhenius definition if you look closely. The Arrhenius definition doesn't say that it contains hydroxide. It says it produces hydroxide. So of course if it contains hydroxide like sodium hydroxide, calcium hydroxide, the NaOH will yield an OH. But it doesn't necessarily mean that it has to contain it. Arrhenius definition simply says that it has to produce it, which it does. There you go. So look for those. Now how then can we tell basically how weak or strong is a particular acid or base? So what we're going to do is going to look at a particular variable that tells us how much of this H plus or OH minus has been produced. Remember, the strength of an acid or a base is dependent on how much H plus and how much OH minus is produced. So if we have a strong acid or base, that means all of it is produced. So whatever the concentration of your acid, you're going to get 100% of it here as your H plus. Whatever the concentration of your strong base is, you're going to get 100% of it here. Well, this weak acid or base does not give you 100%. It gives you significantly less. Average of 5 to maybe 12% ionization. So exactly how much do you get? Well, that's what is to be determined using a special calculation using an ice box. Okay? So you may or may not be using that. If you're using it, then that's how you'll be able to determine exactly what the concentration of H plus and OH is. And what we actually do use then to find out to what extent then, if not 100%, has this acid ionized? To what extent has this base ionized to produce hydroxide, if not 100%? What variable will help us at least gauge that? It's called Ka, the ionization constant of acids, or Kb's, the ionization constant of bases. And all they mean is that if Ka times Kb is just like a representation of H plus and OH minus, that should tell you that they indeed should form Kw, or 10 to the negative 14, just like they did right up here. Which means that if you were to take the pKa plus pKp, you would find pKw, and that would equal 14, just like pH plus pOH is equal to 14. So last little bit, pH plus pOH is equal to 14, just as pKa plus pKb is equal to 14, just as H plus times OH minus is equal to 10 to the negative 14, then Ka, which represents H plus, times Kb, which is a representation of OH minus concentration, should also give you 10 to the negative 14, which is of course Kw.